One of the things that we can do with our limit definition of a derivative, showing that a function is differentiable at a point, is we can use it to prove that a function is differentiable at a point in a very similar way to how we showed that a function was continuous at a point. So let's take a look at a piecewise function here, and let's ask ourselves, is the function f of x, and it's going to have two pieces. It's going to be the linear piece for x less than 2, and then it's going to be the quadratic piece x squared plus 4 for x greater than or equal to 2. And we want to know, is this function differentiable at x equal to 2? In other words, if I were to graph this function, would the derivative, the rate of change at that instant x equals 2, would that exist? Well, in order to show that, what we need to show, if you go back especially to that alternate form for the limit definition of a derivative, we need to show that the limit as x approaches 2 of f of x minus f of 2 over x minus 2 exists. And this is that alternate form for the definition of the derivative. We said the limit as x approaches a of f of x minus f of a over x minus a, where a is this value 2 right here. So we want to show that this particular thing exists. Just like with continuity, if I want to talk about the limit as x approaches 2 of a piecewise function that's one thing to the left of 2 and another thing to the right of 2, I need to look at the one-sided limits of this particular statement. So let's see what happens here when I look at the limit as x approaches 2 from the left of f of x minus f of 2 over x minus 2. Well, I know that if I look at what f of x is, x approaching 2 from the left, values less than 2, the function for less than 2 behaves like 4x. So f of x to the left of 2 is 4x. F of 2, in fact, I'm going to go ahead and write it over here because we're going to need it for the other side as well. F of 2, where x is equal to 2, I plug it into x squared plus 4, 2 squared plus 4, f of 2 is equal to 8. And I'm going to write it over here because it comes up for the right side limit as well. So f of x minus f of 2 looks like 4x minus 8 over x minus 2. Well, I can't evaluate it yet through direct substitution, because if I substitute in 2, I get 8 minus 8 over 2 minus 2, and I get that indeterminate form 0 over 0. But if I look at the numerator, I can factor out a 4 and say the limit as x approaches 2 from below. If I factor out a 4, I get 4 times x minus 2 all over x minus 2. And the x minus 2's will divide out. So this is the limit as x approaches 2 from below of 4, and we know that the limit as x approaches any value of a constant is equal to the constant. So the left-hand limit here, in other words, the rate of change as we approach it from the left is equal to 4. So now let's apply the same logic and look at the limit as x approaches 2 from the right. Again, of the same expression, f of x minus f of 2 over x minus 2. Well, this is the limit as x approaches 2 from above. Well, now for values to the right of 2, f of x is x squared plus 4. So I need to put x squared plus 4 in for f of x, minus f of 2, which we established was 8, all over x minus 2. And if I clean up that numerator, I get that this equals the limit as x approaches 2 from above of x squared minus 4 over x minus 2. And again, direct substitution is going to give me 4 minus 4 over 2 minus 2. So again, I need to look to some algebraic technique, and this numerator factors as the difference of squares. So I have the limit as x approaches 2 from above of x plus 2 times x minus 2 over x minus 2, which when those divide off, I get the limit as x approaches 2 from above of x plus 2. Now I can do that through direct substitution and say that's 2 plus 2 equals 4. And in fact, I get the same value from the left and from the right. So as I approach it from the left, where I'm that linear piece 4x, the rate of change is 4. And in fact, we knew that because we know the rate of change of a linear piece just by looking at it, but we verified that it's 4. Over here, the quadratic piece, as I approach 2 from the right, that quadratic piece also has a rate of change at that exact instant of 4. And so because the limit as x approaches 2 from below of f of x minus f of 2 equals over x minus 2 equals 4, which equals the limit as x approaches 2 from above of f of x minus f of 2 over x minus 2. So because the one-sided limits match, we can say that the limit as x approaches 2 of f of x minus f of 2 over x minus 2 equals 4. And so the question was, is it differentiable at x equals 2? The answer is yes. F prime of 2 is equal to 4. And we were able to show that using the one-sided nature of limits with that limit definition, just like we did with continuity. So we can actually use this idea to verify that a function is in fact differentiable at a point. And we can now say, without having to go through it again if we needed to, because it's differentiable at 2, we can also now say automatically that the function is also continuous at x equals 2.